Welcome to the RACI Future of Polymer Science Festival. This is our first one, and hopefully COVID won't make us have more of these, but I think it's a really nice way of connecting with the polymer community without us being able to have an APS. So before I start, I'd just like to acknowledge the traditional owners of the land where we're all sitting today, and that's going to change depending on who you are. And pay my respects to their elders, past, present and emerging. And I think while COVID has done many negative things, one of the positive things for me is it's made me really value the parts of my personal and professional life which are really great. And one of those for me is the polymer community. We have an amazing polymer community in Australia. And the APS is a really great way of coming together and connecting with colleagues, seeing some amazing science, both domestic and internationally, but also really hearing from our young emerging researchers. So the Polymer Division Committee really felt like we really were missing that. And while we can't perhaps do the networking quite as easily, we can do those last two. So that's what the idea of these 4 sessions are. So every Friday for February, hearing from some amazing international and domestic researchers and connecting with our young researchers and hearing the amazing things they're doing. So we have a very tight time frame. So what I'll do is I'm going to kick off. If you do have questions, put them in the chat and we'll try and ask them if we have time permitting. And yeah, and if I give you a wave if you're one of our speakers, that means you've gone past your allotted time. And please be quicker about completing the rest of your talk so that we don't get very, very far behind. Because Chris is never going to let me live that down if I if I blow out the time frame. All right. So can everyone see my slides? Hopefully they can. So my first speaker today to kick us off is Dr. Brett Fors, and he is an associate professor in the Department of Chemistry and Chemical Biology in Cornell. You can see a little bit of his track record there, which is amazing and has a number of brilliant awards. But I'm sure he's going to tell us all about what he's been doing. So please, Brett, take it away.
Yeah, thank you so much, Georgina, and thanks for the invitation. I think this is really great. I mean, I guess I've been to 2 APS meetings in the past, and the polymer community in Australia is really fantastic. I mean, I was a postdoc with Craig Cocker, so another connection there as well. So I thought I'd tell you a little bit about some of the chemistry that we're doing here at Cornell. I'm actually in my basement right now. We got a boatload of snow this last couple of days, so we had about almost a meter, which is quite a bit. But it's probably much warmer in Australia and probably a much nicer place to be right now. So, as some of you may know, my group is a synthetic polymer group. I'm a synthetic chemist by training, but really kind of merging into more polymer chemistry and doing a little bit of everything from polymer chemistry to some polymer physics to other characterization techniques. And so, you know, there's 4 different areas that our group kind of works in, and we're branching out into some other things, but I'm just going to tell you one short story today about some of our stimuli regulated polymerizations, and that's this first area here. And we want to control polymer chain growth with some type of external stimulus, and the question is, how do we take advantage of this, and how do we start using this to control polymer structure? And so hopefully I can show you how we do that today. But at the very end of my talk, the other thing I'm going to do is talk about some of the things that this has led into, and not stimuli control polymerizations, but we ran into some issues with some of our ionic polymerizations, and really how we've been trying to make more user-friendly cationic polymerizations, because these things have given us a really hard time, both cationic and anionic. And so we've really tried to take that and make these a little bit more user-friendly. We also work on molecular weight distribution. We want to start using, you know, the higher moments of the distribution function, and how can we use that to control polymer properties, and really go beyond, you know, things like MN and dispersity, and use molecular weight distribution shape. And then we also have a small program in electronic materials, and then I would say a growing program in biorenewable polymers and sustainable polymers and trying to do a more circular economy. I think this is a really important problem and something that we will continue to work on and hopefully continue to grow in. But today I'm just going to tell you about some of our stimuli regulated polymerizations. So, like I mentioned, we want to start controlling polymer chain growth with some type of external stimulus. And one of the stimuli when we first started out at Cornell, which I guess was 6 years ago now, was visible light. And the reason we like visible light, right, is that it's incredibly easy to implement. We don't need a specialized setup. We don't need specialized glassware. It's adaptable, so we can change wavelength and intensity, which are parameters that we think we can actually start using to control polymer structure. And then of course, it provides spatial and temporal control. So not only when you shine the light, but where you shine the light, polymerization should occur. And we really thought there was a lot we could do with this. Of course, we're definitely not the first people to think about photo-controlled polymerizations, photo-controlled radical polymerizations. As many of you know, right, in the last 10 years has absolutely exploded. And I think it's just because there's so much that you can do with this, right? So the Hocker group has done some really great photo-controlled radical polymerizations, the Boyer group, the Johnson group, all of these examples. And when you have true photo control, there's a number of applications that you can use this type of chemistry for. But there was one gap when we started, and that was, beyond photo-controlled radical polymerizations. And one of the questions we asked was, how do we go beyond this, and how do we develop, say, photo-controlled ionic polymerizations? And this was kind of our first foray into these ionic polymerizations. And specifically, we wanted to do photo-controlled cationic polymerizations. So I guess the question is why would we want to do this, right? We already have all these really great photo-controlled radical polymerizations. What's going to be the advantage, or why would we even want to develop a photo-controlled cation polymerization? And we really had two motivations initially when we started in the lab. And the first of all, it's going to extend the scope of these processes, right? Because monomers you polymerize via cationic mechanism are very different than monomers you polymerize via a radical mechanism. But more importantly, what we were thinking about initially was, let's say we could switch between a cationic chain end and a radical chain end in situ by using our external stimulus. And if we could do this, maybe we could actually switch monomer selectivity on demand and start controlling polymer structure by just changing our external stimulus. So same solution conditions, but actually just change our external stimulus. I'm gonna select the laser pointer and make it a little bit easier to see. There we go. Okay, but before we get into that, there's one thing I quickly want to define, and that's the difference between a photo-initiated polymerization and a photo-controlled polymerization. So as many of you know, right, the photo-initiated cationic polymerizations have been studied for a long time and are really important processes used industrially for photolithography and coatings and other random things like that. But in a photo-initiated polymerization, you have an initiator, you hit it with a photon of light, and then polymerization starts. So the advantage here is you get chemical amplification. So for every photon you put in, you get many chemical events. But the disadvantage is you only have control over the chain initiation step. And if we really want to start, say, switching polymerization mechanism on demand, this isn't going to work. We need to go beyond photo initiation, and we want to develop photo control polymerizations. So we want, in a photo control polymerization, we want each one of our monomer additions, or about each one of our monomer additions, to be mediated by a photon of light. Now, theoretically, what this allows us to do is say control the rate of polymerization by the amount of light we put in, and turn off one stimulus, turn off that polymerization, apply a second stimulus, and possibly change the identity or the chemical identity of that chain end to actually start switching reactivity on demand. Okay, but how do we do this, right? Before we get to this, how do we develop a photo-controlled cationic polymerization? So from a very cartoonish fashion, this is what we need. We need a stable and dormant polymer chain that when we hit with light, we need this to generate a cation. And of course, the cation that we generate, right, needs to go into a controlled cationic polymerization. Because if it goes into an uncontrolled polymerization process, it defeats the purpose right away. And then importantly, right, and I think this is the most important step, is when we turn the light off, this needs to go back to the same stable and dormant species. So how do we photoreversibly generate a cation with light? And how do we shuttle this into a cationic polymerization? So to answer the question of how do we shuttle this into a controlled cationic polymerization, we were really inspired by this work by Kamagaito, where they developed this cationic raft or reversible addition fragmentation chain transfer polymerization of vinyl ethers that was initiated by strong acid. And as I mean, this this audience is, I'm sure, very familiar with RAF polymerizations. But the thing we really liked about these cationic RAF polymerizations is that any one time, right, we only have parts per million or a very small concentration of the propagating cation. And then the remaining actually is these dithiocarbonyls. And then because this addition fragmentation process is faster than propagation, all of our chains grow at a similar rate. But what we thought is, you know, for this mechanism, we might be able to render this photocontrolled by simply just photoreversibly shuttling in parts per million of a cation into this mechanism. And if we can do that, right, we might be able to make a photocontrolled cationic polymerization of vinyl ethers. Now, the other thing that we really liked about this Kamagaito chemistry is we thought that we could use their chain transfer agents, or these dithiocarbamates, as our initiating species as well. Because what you can imagine, right, if you take this dithiocarbamate in the presence of a very oxidizing photocatalyst in the excited state, this should get oxidized to the radical cation. And then you could imagine, right, you can imagine that that radical cation should very quickly undergo a mesolytic cleavage event to generate this oxocarbenium ion. The oxocarbenium ion is just the propagating chain end of the cation polymerization of vinyl ethers. So that will shuttle into our RAF process and give us a controlled polymerization. And then the other species that we get from this mesolytic cleavage is this dithiocarbamate radical species. So this species is not terribly nucleophilic, shouldn't do a fast addition to an olefin, actually should dimerize to the disulfide faster than that. But for this to turn over our photocatalyst, what we hypothesized would be that this reduced photocatalyst would come back in contact with either the disulfide or this dithiocarbamate radical, reduce it to the anion, which then will cap our propagating cation and feed us back to the same stable and dormant species, as well as turn over our photocatalyst. And then this whole process can be mediated by an additional photon of light, and we should be able to reinitiate those polymer chains. Now, the other thing we like about this mechanistic hypothesis is that when we turn the light off, right, we no longer have the photocatalyst in the excited state. And so all of our propagating cations should feed back to the stable and dormant species, and the polymerization should stop. And the other thing I should say is this will not irreversibly terminate the chain ends, right? So this is a reversible termination, because as soon as we turn the light back on, we re-excite the photocatalyst and reinitiate polymerization. And then the last thing I'll point out here is our other hypothesis was that this cation concentration at any one time should be directly proportional to the amount of light that we put in. So we should be able to control the rate of polymerization by the intensity of irradiation, and that should give us perfect temporal control over polymerization. Okay, so to make a long story short, this works quite well. This hypothesis works. So we take isobutyl ether as our monomer and use this dithiocarbamate, which we call 2A, as our chain transfer agent, as well as our initiating species. And then we use this photocatalyst, which is one here, this beryllium complex, or this beryllium salt, as our photocatalyst. So these are really interesting photocatalysts. They're very oxidizing in the excited state. And when we irradiate these reactions with light, we get really good control. So experimental and theoretical molecular weights match up very nicely. We get relatively narrow molecular weight distributions. We can change the average molecular weight by changing the chain transfer agent to monomer ratio. So just characteristic features of a controlled polymerization process. And then just a couple of control experiments. Without light, we don't see any polymerization. Without photocatalyst, we don't see any polymerization. So that was good. But the real question is, right, we don't want just a new photocontrolled, or just a new controlled cationic polymerization. We want photo control, right? So can we turn this polymerization off and on with light? And can we control the rate of polymerization with the amount of light we put in? Because that's really going to be key if we want to actually start using this in the future. So we take our standard conditions, we turn the light on, and polymerization starts. Then when we turn the light off, polymerization stops, and we can do this multiple times. Each time in the presence of light, we see polymerization. Each time in the dark, we see the absence of polymerization. Now, even what you'll see here is that we still maintain control. And so this suggests that we're not irreversibly terminating our polymer chain end, and that it supports our mechanistic hypothesis. Now, the other thing I want to point out here, and this is kind of a side note, and this is something I'll come back to at the end of my talk, is you'll notice that it looks like we have a small induction period at the beginning of these reactions. And this goes back to how sensitive ionic polymerizations are, and these induction periods are usually just caused by small amounts of nucleophilic impurities. And so this really is where we started thinking about, can we make more user-friendly cationic polymerizations? And I'll talk about our work in that at the very end. Okay, so we can turn this on and off with light, but the other question is can we control the rate of polymerization? And so what we find is that we're actually first order in light. So we can precisely control the rate by the intensity of irradiation. And so this opens up a number of applications for, say, patterning, where we can control the rate at the propagating chain end by the intensity of irradiation that we put in. So this is exciting, right? But now how do we start taking advantage of this? How do we actually start using this to start controlling polymer structure? And I mentioned early on in the talk that one of our grand challenges was, can we actually use these photocontrol polymerizations to start controlling the identity of the chain end and actually switch our polymerization mechanism and monomer selectivity on demand? And so we know, or I just showed you, right, that when we oxidize these chain ends with a very oxidizing photocatalyst, we generate a cation to a photocontrolled cationic polymerization. And of course, CSIRO Boyer and Jeremiah Johnson have shown that when you reduce these chain ends, you generate a radical species and do a photocontrolled radical polymerization. And so what we asked is, can we put two different photocatalysts in solution, one that's oxidizing in the excited state, one that's reducing in the excited state? And if we can selectively excite each of those photocatalysts, perhaps we can actually start switching polymerization mechanism by just changing the wavelength of irradiation. So that was the idea, right? And for this to work, we chose two different photocatalysts. So the first photocatalyst for the cationic polymerization, we stuck with our beryllium salt, right? It works really well for cationic polymerization. And then for our radical polymerization process, we chose iridium pippy. And so this is iridium pippy. Now there's a couple of reasons we chose this catalyst. First of all, it's very reducing in the excited state. CSIRO Boyer has shown that it's very efficient in these photocontrolled radical polymerizations. But also, if you look at these two UV vis spectra of these two photocatalysts, there's this very small window where we thought we could irradiate with green LEDs, selectively excite the beryllium complex, promote the cationic polymerization. And then if we switch to blue LEDs, we should excite both photocatalysts and promote both the cationic and the radical polymerization at once. Okay, so now we have everything in there at once, right? So we have both photocatalysts, the beryllium salt, the iridium complex, methyl acrylate, which of course polymerizes via a radical mechanism, and isobutyvinyl ether, which polymerizes via cationic mechanism, and our chain transfer agent. So in this case, we're using a trithiocarbonate. And when we take this mixture and we irradiate with just green LEDs, we just excite the beryllium complex, and we get just polymerization of isobutyvinyl ether. So we only see conversion of IBVE, and we see no incorporation of methyl acrylate. So this suggests that we're just doing the cationic polymerization and we're not generating any radicals at the chain end that's allowing us to polymerize the methyl acrylate. Now, if we take the exact same solution conditions and we first irradiate with green LEDs, and then at about, say, 80% conversion, we switch from green LEDs to blue LEDs, what starts happening is we start to photoexcite our iridium complex, and we start to reduce some of our chain ends, and you can see that our methyl acrylate starts to grow in. And so what we're doing is we're polymerizing the methyl acrylate. We make these relatively well-defined tapered diblock type structures. And this was a very exciting day for our lab, especially when we were first starting out, right? Because this is the first example where we showed that we could actually switch polymerization mechanism by actually just changing our external stimulus, right? We're not changing the solution conditions at all. We're simply just changing how we apply the external stimulus. Now, if we just take blue LEDs or just take the same reaction and just excite this with blue LEDs from the start, we get a multi-block copolymer, because now we're exciting both photocatalysts at once. And so on average, we get a pentablock copolymer, but it's not a well-defined pentablock, right? Because what we're doing is we're going along and doing radical polymerization. Every once in a while, it switches to cationic. Every once in a while, it switches back to radical. And so this is not a well-defined multi-block copolymer. We probably have some diblock in there. We probably have some decablock in there, because it just stochastically switches back and forth. And so this is not ideal, right? We want to be able to switch back and forth on demand. And we want to be able to do this with precise control so that we can control the length of each block as well as the total number of blocks. And we want to make a homogeneous mixture of all of these multi-block copolymers. Now, the reason we can't do this with our initial photo system is because we don't have orthogonal stimuli. Because when we irradiate with blue LEDs, right, we're exciting both photocatalysts, both the cationic and the radical polymerization are being promoted at once. And so that doesn't allow us to actually switch back and forth on demand. So we went back to the drawing board and we thought, okay, how do we do this, right? What we need to do is have two completely orthogonal stimuli that allow us to independently promote either the cationic or the radical polymerization at once. And that's what's going to give us the most control in these systems. So how do we do this? So if we want to continue to do our radical polymerization with photochemistry, right? It's very well behaved and we know it works very well. Can we develop a cationic polymerization that's actually mediated by some other stimulus that's orthogonal to light? And we have a really fantastic colleague, Song Lin, in our department. And so we started collaborating with him and we started asking the question, can we develop an electrochemically controlled polymerization or electrochemically controlled cationic polymerization, which should be completely orthogonal to light or to photochemistry? So here was our idea, right? So if we take our photocontrolled cationic polymerization, we simply remove the photocatalyst from the system, but then just add in, instead of the photocatalyst, use an electrochemical cell. And the idea here, right, is if we apply an oxidizing current, just like in our photocontrolled system, we should be able to oxidize this dithiocarbamate at the electrode surface, generating this radical cation. And in the same way, that radical cation should still undergo the same mesolytic cleavage to generate our oxocarbenium ion, which then will just simply go into our photocontrolled into our RAF mechanism. Now, you will have some of this dithiocarbamate radical sitting around, but our hypothesis is this will just dimerize to the disulfide and sit there. And then also the cation concentration at any one point should be directly proportional to the amount of current density we pass. So we should be able to control the rate of polymerization by current density as well. And then if we want to turn this off, all we have to do is reverse the current in the cell, reduce what's now probably the disulfide back to the anion, which will cap our propagating cation and get us back to this stable and dormant species. Okay, so that's our hypothesis. And again, we basically did the exact same thing. We took our photocontrolled cationic polymerization conditions, we removed the photocatalyst, put this in an electrochemical cell. We tried a lot of things here and nothing seemed to quite work. Now, in all cases, when we applied an oxidizing potential, we did see polymerization. However, unfortunately, we always saw very broad molecular weight distribution. So you can see here our dispersity is about 2.3. But it wasn't just broad molecular weight distributions, it was actually bimodal molecular weight distributions. So the first mode was actually a relatively well-controlled polymerization, which was promising, but the second mode was a really high molecular weight polymer, and that polymer was actually plating on the electrode. And so when we're thinking about this, what's causing this polymer plating and what's causing this really high molecular weight polymer to form? And so what we thought is it could be the fact that we're doing this oxidation event inside the electrochemical double layer. And when we do that, we're depleting all of the dithiocarbamate. So we're generating a high concentration of cation at the surface, and then that's just initiating an uncontrolled cationic polymerization, which is leading to, very fast formation of high molecular weight polymers, which then are just crashing out onto our electrode surface. So the question is, how do we get around that? And if we look at our CV, right, this makes sense, right? The oxidation of our chain transfer agent is irreversible. So as soon as you oxidize it, it's undergoing mesolytic cleavage and then probably just decomposing. But how do we remove this oxidation event from our electrode surface? And one way we could do this is use an electrochemical mediator, right? So if we put a mediator into solution that basically will go on the electrode, get oxidized at the electrode surface, diffuse away from the surface, and then do the oxidation of our chain end in solution, this way we won't get that high concentration of cation at the electrode surface, and we won't initiate that uncontrolled polymerization at the surface as well. And the mediator we chose to start with was TEMPO, right? So TEMPO has a very reversible redox couple, and it's about 200 millivolts easier to oxidize than our chain transfer agent, which thermodynamically is right where we want to be for a mediator. And so this should work well. And it turns out this works great. So here's a very small table, but in our first example, right, we don't have any TEMPO. We see this very broad molecular weight distribution. When we simply add in 1 mole percent TEMPO, what you can see is that bimodal molecular weight distribution actually completely goes away, and we get very well-controlled polymerizations. Okay, so that was exciting. Now we at least have electrochemically initiated cationic polymerization. But the next question is, can we turn this on and off, right? Do we actually have temporal control using electrochemistry? So if we apply an oxidizing current, polymerization starts. I've already shown you this, but then we reverse the potential in the cell, apply a reducing potential, and polymerization stops. And again, we can do this multiple times, just like in our photochemistry, and we get excellent temporal control. We can also control the rate of polymerization by the amount of current we pass. And so this really allows us to control the identity, or the temporally control the cationic polymerization. Okay, now the reason we developed this, right, is we wanted to pair this with our photocontrolled radical polymerization. But those of you that are paying attention will notice, right, there's an issue with this, because the mediator we chose was this aminoxyl radical, right, or the temple radical. And as soon as we start generating radical species with our photocontrolled radical polymerization, this aminoxyl radical will just come in and basically cap our propagating chain ends. And so it's going to terminate our radical polymerization. So not only do we need orthogonal mediators or orthogonal stimuli, but we also need compatible mediators. So we need to go back to the drawing board, and we thought, what other mediators could we use? And one that we'd always talked about a little bit was ferrocene. Ferrocene also has a very reversible redox couple. It's been used a lot as an electrochemical mediator. Now, the reason we didn't originally choose to use this is because, as you can see here, right, it's about a half a volt easier to oxidize than our chain transfer agent. Now, initially, we thought that'd be pretty bad, right? Because thermodynamically, it's not going to be very favorable to oxidize our chain end. But as all of you know, right, we need only a very small concentration of propagating cation to get this RAF mechanism to work. So even if thermodynamically it's not very stable, as long as we generate a very small concentration of this cation, it actually should still lead to controlled polymerization. And it turns out this works incredibly well. So adding in 0.01 mol% of ferrocene, we can actually get very well controlled cationic polymerizations that are at least initiated by electrochemistry. And then if we just switch the potential, or the direction of the current in the cell, we can turn this on and off. And again, we can control the rate of polymerization by the amount of current that we pass. And so ferrocene actually turns out to be a really well-controlled electrochemical mediator. Now, the other thing that we like about ferrocene is that the ferrocenium, right, whatever you oxidize at the electrode surface is also isoluble. And so we thought we actually could be able to take this and develop a chemically controlled cation polymerization as well, right? Because in the same way, right, if we're not in an electrochemical cell, if we simply just add in a small amount of ferrocenium, this should oxidize our chain end, again, to get that same radical cation, which will give us our oxocarbenium ion and initiate polymerization. And then if we want to turn this polymerization off, all we have to do is add in an equimolar amount of this dithiocarbamate anion, which will cap our propagating cation and reduce any remaining ferrocenium back to ferrocene and halt the polymerization. And so again, will this work? And it turns out this works really well. So we remove this from the electrochemical cell, and we just add in a very small amount of ferrocenium tetrafluoroborate to initiate the polymerization. Polymerization works incredibly well, very well controlled. We can control the rate by the amount of ferrocenium that we add. And we can effectively turn this on and off by simply just rotating the addition of the ferrocenium and this dithiocarbamate anion. And so we have very good temporal control. And so this is just more of a chemically controlled process. Okay, so here's the next question, right? Can we actually start using this to switch polymerization mechanism? Can we pair this with our photocontrolled radical polymerization process? And can we actually start making multi-block type copolymers? And so to get this to work, right, what we need to do is have everything in there at once. And if we want to initiate the radical polymerization, all we have to do is shine light, and we'll start polymerizing methyl acrylate. Then if we turn the light off, we'll reversibly terminate the radical polymerization. We add in a small amount of ferrocenium, we should initiate the cation polymerization. And then to turn off the cation polymerization, all we have to do is add in the dithiocarbamate anion. This works very well. We can make multi-block copolymers, right? So we can first do cationic or radical followed by cationic followed by radical polymerization, or we can do the opposite, same solution conditions. The only thing we're changing here is the order in which we apply the stimulus. Now, the other thing I want to point out is the length of each one of these blocks is dictated by the number, or by the amount of time we apply a stimulus, and the total number of blocks is dictated by the number of switching events that we put in. And so this really allows us to make any multi-block that we want. Okay, but here's the other question, right? We developed this, Georgina, is my time up? Okay, awesome. I will finish up in the last 2 minutes. I'll show one other thing and then I'll finish up. So one other thing I noticed here, or what I was talking about, is we developed this electrochemically controlled cationic polymerization to actually pair it with our photocontrolled radical polymerization. And one thing you'll notice, we actually switched to the chemically controlled polymerization to actually start switching back and forth on demand. But chemically controlled is not great, right? Because you're still adding exogenous additives to the reaction, and that can cause termination events. The problem is when we did this in electrochemical cell, it completely shut down our photocontrolled radical polymerization process. And you know, these conditions are almost identical. So the question is, what's going on here, and why are we stopping this polymerization process? And it turns out, you know, what happens is it just completely shuts down the radical polymerization. So what's the difference here? And the only difference between these two processes was the concentration of ferrocene that we had in there. So for our electrochemically controlled polymerization, we had higher concentrations of ferrocene. Turns out ferrocene is actually a very good triplet quencher. And so it's actually quenching the excited state of our iridium complex. So this is just a Stern-Volmer plot, shows that it's a very strong quencher. And so to get around this, all we have to do is lower the concentration of the ferrocene in our electrochemical cell. And this turns out to work very well. So the activity of our radical polymerization comes back. And now we can pair our electrochemically controlled cationic polymerization with our photocontrolled radical polymerization. And now we can switch back and forth without touching solutions at all, right? We're simply just turning switches and turning knobs, and we can make any multi-block that we want. And we should be able to start using this to start controlling other polymer structures, right? So we're using this for 3D printing. We're using this to actually insert in, you know, branching groups whenever we switch the stimulus. And so hopefully what you see here is there's a lot of opportunity to start taking advantage of multi-stimuli systems to control polymer structure. Okay, so I'm gonna skip this stuff. I talked way too long, but the last thing I need to do is I just need to thank my group. I have a really fantastic group of people, and they have done amazing, especially even through the whole COVID situation. They have been absolutely fantastic, and I can't tell you how thankful I am for my group, and also with my family. I haven't traveled much this year, and like Georgina said, it, you know, the one thing about COVID is it really does make you realize like how important and how lucky we are, right? And so I've been really fortunate to get to spend a lot of time with my family, and I've really enjoyed it. It's actually been there have been some very good things about this year, right? Some very difficult things, but also some very good things. Thank you again for the invitation. I really appreciate it, and I think this is a really great program.
Brilliant. Thanks you so much, Brent. That was a really interesting talk. I like so many questions, but we do actually have a couple in the chat, so I don't get to ask mine. And James is going to start us off. So he wanted to know, does the difference in the molar absorptivity, can you see this question? Of the two photocatalysts have a huge influence on your switching? What about depth penetration difference in your?
Yeah, that's a really good question. So, so one big thing is we have to have because of this, right? If we have very different molar absorptivities of our two photocatalysts, we have to have extremely good stirring in the reaction. Otherwise, that has a huge influence, right? Because one photocatalyst will absorb everything before the other one. And so good stirring actually gets around it. You know, the other problem, and this isn't so much molar absorptivity, but it's kind of the orthogonality. We would love to have a completely orthogonal photo system where we basically have two photocatalysts that their absorption spectra are completely not overlapping at all. Now, we can do that, we can find two, but the issue we've ran into is not so much with the molar absorptivity, it actually has to do with the energy transfer. Because what happens even when we excite the photocatalyst of you know, higher energy light, we get energy transfer to the lower one. Because not only do you not have the absorption spectra overlap, you can't have the fluorescence spectra overlap at all either. And so that's been a challenge. So if anybody has ideas of how we could actually get two photocatalysts that are completely orthogonal, that would be fantastic too.
All right, we only have, I'm sorry that we're not going to be able to ask you all these questions. We only have time for one more question. And that is there any limitation in the size of each block?
Yes, so the major limitation, that's a really good question, is actually on the smaller end. So the size of the block is, even when we start getting down around 1 kilogram per mole, it starts to not be as efficient as it should, because what happens, right, is these are still stochastic. And so you get some polymers that have, you know, 5 monomer units, and some polymers that have 0, and some that have 10. And so it's not ideal. We'd love to be able to start getting towards sequence control polymerizations, right? And we can't do it with this system. And so for that, we're actually going to 3 stimuli systems, and we think we maybe can use that to actually get to sequence control polymerizations, because we really need to add 1 monomer unit at a time and then use the second stimulus to deprotect that chain end. So that's the big limitation, is actually on the smaller side than the larger side. That's a really good question.
Brilliant. Now, I'm sorry, we don't have time to ask any more questions. So we just have to thank Brett again for a really interesting and so applicable talk. So please join me in just giving Brett a hand. And thank you. And now we need to move on to our next speaker. So Brett, I will, if you can stop sharing your screen. And
yep, absolutely.
Sorry, let me try. Can you see the screen? Can you hear me, Georgina?
I can hear you.
Okay,
okay, I was going to introduce you, but that's fine. You're here already. So this is Dr. Chin Ken Wong, who is a postdoc, I believe, from UNSW.
Yep.
Brilliant. Please,
right.
Please start.
Sorry, just trying to try to fix the screen. All right. So thank you for the introduction. So today I'm going to talk to you about a class of particles known as polymer hexosomes. So they're basically particles that look like this on the left. And I'll share a few findings on how these particles exhibit something known as topological defects. Now I'm going to start off by bringing up the word defects. So I'm sure if most of you here today, when you hear the word defects, you naturally associate it with something which is, negative or undesired. And if you, for instance, come across, cables that are defective like this at home, your first instinct would be to, get rid of it because 1, it doesn't serve its function anymore, and 2, it's dangerous. Now, I hope to convince you by the end of today's talk that not all defects are necessarily bad. And in some cases, defects can actually appear to be quite aesthetically pleasing or sometimes even useful. Now, what does it actually mean when you add the word topological in front of defects? Now, unlike a common defect, for instance, a defective wall with a crack in it, this here is something that you can patch. And if you patch a wall, you essentially restore the function of the wall because you restore its structural integrity. Now, unlike this example here, topological defects are features of a system that cannot be removed, meaning you're not able to patch a topological defect, such as in this case. Now, if you don't understand this statement, don't worry about it. I'll share with you something known as the Hairy-Ball theorem. So the Hairy-Ball theorem is derived by this man here, and it literally means what it says. It's about a ball which is hairy. So imagine you take a ball with random hair strands sort of sticking out the surface. And if you were to take a comb and you were to comb the hair strands from the left to the right across the center and around the back as well, you find that it's quite easy to have the hair strands all sort of lie flat or tangent to the surface. And as you move away from the center, it's still possible to do so. But as you approach the north and the south poles, you will always end up with hair strands that stick out perpendicular to the surface. Now, these 2 points at the north and the south poles, these are essentially topological defects. So in other words, topological defects are simply points of discontinuity in an ordered system. So here the order arises because you took a comb and you combed the hair strands in one direction. And trust me, regardless of how you comb the hair strands on this ball, you will always end up with 2 or more topological defects. Now, topological defects are actually extremely common around us, so much so that they actually appear on the human body. So these are 2 examples of topological defects, fingerprints and as well as hair walls. And the whole point of showing you this is to actually convince you that topological defects are not necessarily bad. All they really do is they give identity to the material. And in some cases, for instance, with a fingerprint, you can actually use it for a certain purpose. Now, today I'm going to talk to you about topological defects in a type of particle known as polymer hexosomes. So this is what a polymer hexosome looks like under a PEM. So you can see that's mainly composed of multiple layers of rings. And these rings, they all align along this central axis of rotation. And if you take this particle and if you rotate it slightly, you can actually look at the cross-section of this particle. Now, what's interesting is that these rings, they actually align adjacent to one another or pack adjacent to one another in a hexagonal fashion. And the reason why these particles are called hexosomes is due to this hexagonal packing that you see here. And what's also interesting is that these rings that you see here, these are actually hollow, so they're solvent-filled channels. So obviously they can be used to accommodate water-soluble materials in addition to hydrophobic materials in the hydrophobic domains. Now, some of you might have noticed that these particles here, they all exhibit a shape that resembles a spinning top toy. And if you look into literature, you find that most, if not all, polymer hexosomes reported to date, they have this spinning top shape. Yeah? So you can see it clearly in these 3 examples. And today I'm going to share with you a different scenario. What will happen to polymer hexosome morphology if the polymer hexosomes have non-circular rings, yet they still possess the central axis of rotation? Now, before I move on to talk about the interesting bits, I'm just going to give you a bit of backstory about how this project started. So a couple of years ago, I was working with this tri-block polymer here, whose chemical structure is actually not terribly important for today's talk. But back then, I was using this for a whole different reason. But I found that this polymer could actually self-assemble into structures that this under certain solvent conditions. And at first glance, you can see that these particles, they have these really complex internal structures. But if you zoom into this region here, you can see here at the periphery of these particles, there's actually cylinders that pack in a hexagonal fashion. So this is obviously reminiscent of polymer hexosomes. But the funny thing is that these particles, they don't actually have a shape which resembles a spinning top, right? So I remember when I first came across these structures, I found them really intriguing, and I tried looking into literature and there was nothing on this. So this prompted me to study these structures in more detail. And one of the very first things I did was to load gold nanoparticles into the system. Now, the whole point of loading gold nanoparticles is to increase or enhance electron contrast. And this allows us to basically visualize these particles in more detail. And I'm going to skip through the chemistry here in the interest of time. This is fairly basic chemistry, but what we basically did is we grew gold nanoparticles selectively within the outer cylindrical face, so the outermost layer of each cylinder. Now, if you look at this image here, you can see here now that the hexagonally packed cylinders, they appear much clearer now. But the best part about doing this is that it allows us to do something known as STEM imaging, or scanning transmission electron microscopy. So STEM imaging is a bit like dark field TM imaging. So all the bright contrast that you see here actually comes from gold nanoparticles. So the nice thing about doing this is that you can actually eliminate noise or electron contrast from all the organic phases. So as I mentioned 2 slides ago, these particles were made using a tri-block polymer. So you don't actually look at the polymer phase, but you look at the gold nanoparticle that sits within the outer cylindrical phase. And the nice thing about doing this is when you zoom into a single particle and you focus around this area, you can clearly see the pattern of the cylinders. So some of you might have noticed that this cylindrical pattern that you see here resembles a fingerprint. So this was the first sign that these structures actually exhibit topological defects. Now, in order to better study this system, we went on to do something known as STEM tomography. So STEM tomography is an imaging technique that allows you to look at the structure in 3 dimensions. So I'm going to play this video once, and just to give you an idea of what you're looking at. So this here is a single polymer hexosome that's being rotated along an axis of rotation. Now I'm going to play this one more time, but this time I'm going to pause it just to highlight certain features. I'm going to pause it somewhere around here. And if you look on the left-hand side, I'm going to bring back the, if you look on the left-hand side, you can see here the presence of cylinders that pack in a hexagonal fashion. So obviously this is consistent with a polymer hexosome morphology. But the funny thing is that these cylinders, they only span across 1, 2, and 3 cylindrical layers. And beyond this, the structure is actually completely hollow on the inside. So what this tells us is that these particles, they're actually a bit similar to polymer vesicles or polymerosomes. So rather than having a bilayer membrane structure, they actually have a hexagonally packed cylindrical membrane. Yeah? And if I play this video to the end, you can see that these cylinders, they actually connect all the way to the front of the particle. And for some reason, they just loop around this area. Yeah? So this point here is obviously a topological defect. Now, the nice thing about doing this is it can convert this raw data into a 3D reconstruction. So this is what the particle looks like from the top down. Obviously not very useful because it's a solid object. But what you can do with this reconstruction is you can slice it into two halves. So across this line, I'm going to bring back my pointer. Yep, across this line. And you end up with two hemispheres. Yeah, so the front half and the back half. So this green point that you see here is actually this defect here. So what this data tells us is that there's actually another defect that's at the back of the particle, somewhere behind over here. Now what I'm going to do is I'm going to play this tube series or this video one last time. But this time I'm going to have an animation here just to help with visualization. And I'd like you to pay attention at the start of the video. So you'll see very broad U-shaped cylinders at the back of the particle. I'm going to play this now. So you're going to see U-shaped cylinders at the back. Yeah, really broad U-shaped cylinders at the back. And that's consistent with the defect that's at the back of the particle. And the whole point of showing you this is to actually convince you that these two defects are interconnected. So each and every one of these rings that you see here in this model here, they all have to look around these two topological defects. Now this here is the model which is used to prepare the animation in the last slide. And I've already convinced you or shown you that using this data, we can prove the existence of this blue and this green topological defect. But if this model were to be true, we should technically see two more defects at the left and the right polar ends, right? So unfortunately, due to instrument limitations, we can't actually visualize these 2 points in the 3D reconstruction. So if you look at this reconstruction on the right here, you can see that the reconstruction is actually very blurred out over here because we're missing a lot of data. So in order to solve this problem, we went on to look for a different particle where one of the defect faces the operator at the start of the experiment. And simply by tilting the particle 40 degrees, you can see here the presence of a left polar defect. So you can see here it's clearly consistent with the model. But again, due to instrument limitations, we can't actually visualize the right polar defect that's over here. But we know by intuition, since defects has to appear in pairs, if you can see one of them, there has to be another one on the right polar end. And all in all, our particles basically have a defect structure that's similar to a baseball. Yeah. So just very quickly, I'll finish in 1 minute, sorry. So what's also interesting is that when you look at these particles under an SEM, you can actually identify the defects on the surface as well. And some of you may be wondering, all right, these are nice particles, but why spend so much effort to study them? Now, a recent paper by the Swagger group, they showed that topological defects, for instance, this point here, can actually be used to spatially anchor materials. So from a drug delivery perspective, these are extremely exciting because you can, for instance, attach targeting ligands at specific sites on the particles or at the defects, and you can force particles to orientate in a certain manner when they're interacting, for instance, a cell receptor. Right? And yeah, I might skip through this summary. I'll just quickly run through this summary. So I've introduced to you a new class of polymer hexosomes with 4 topological defects. And the key difference between our particles is that our particles have non-circular rings with a 2-fold rotational axis. So you can rotate the rings twice in order for it to return to its original position. Whereas in the case of classic spinning top polymer hexosomes, the rings are always circular and they have this infinite rotational axis. And last but not least, I showed that polymer hexosomes are not necessarily solid structures as previously taught, and they can also be fascicular. And with that, I'd like to thank a couple of people. So I'd like to thank the organizing committee for giving me the opportunity to present today. I'd like to thank my collaborators, my mentors, and these funding bodies, especially the Humboldt Foundation for funding my Humboldt Fellowship for 1.5 years. And last but not least, all of you for listening today. Thank you.
Thank you so much. A very interesting talk and some beautiful structures, as you alluded to. Unfortunately, we don't have time for questions. We are running under a tight time schedule, but I'm sure if you're interested in asking any questions, you can email Ken, and I'm sure he'll be happy to answer anything that you have. Okay, so thanks again, Ken. Now our next speaker is Greg Rollo-Walker. He's a PhD candidate from Deakin and CSIRO. So Greg, could you pull up your presentation? Brilliant. Thanks, Greg. feel free to start.
Audio better?
Audio is good.
Ah, perfect. Headphones not working. Yes, so I'm introducing my project, which is looking at the use of these quasi-block copolymers in the use of electrolytes in alkaline metal batteries. And yeah, as I said, this is part of a collaboration really between Deakin University and CSIRO as part of the ARC Future Energy Storage Technology Centre, Store Energy. Just to give you a quick introduction into sort of the battery world. So obviously currently there's issues with flammability in terms of our devices. We're seeing more device fires and things in terms of electric cars as well as mobile phones. And that's really down to the issues of flammable organic solvents in the use of our electrolyte systems. Furthermore, as well as this, we're pushing our devices to go harder and faster for longer, but actually the current technology is really reaching its peak. And so our current technology, we need to start improving this and to improve our devices. So this is where solid state opportunities are. In particular, what we're going to improve is safety initially. We'll take away the organic solvents and replace it with a non-flammable solid alternative. But through the use of solid states, we can also look at using metal anodes in terms of our batteries. And overall, these have a much higher theoretical capacity than current graphite anodes, which are used in lithium-ion technology. So not only can we take the step of increasing the safety in these batteries, but we can also look at increasing performance. And then finally, this brings on to where polymers come involved. So polymer electrolytes have been researched in batteries now for a good 20, 30 years to varying degrees of successes. But really what polymers offer is a huge surplus of monomers available to trial for different types of technology and different types of battery, as well as the flexibility in terms of structures. We can make it into blocks, we can make cone structures and various other different options. Overall though, in terms of polymer electrolytes, there's two areas that really need to be improved. The first of these is the ambient temperature ionic conductivity, and the second is the mechanical strength and mechanical integrity of these polymer films. So this is where block copolymer electrolytes have really been utilized, as they allow us to combine two different properties. So we can have a hard block, which is a high TG polymer such as polystyrene or alternatives. So this will provide the overall mechanical stability for the polymer electrolyte. And then we combine this with a soft block. So this could be something like PEO or even anionic polymer, which will allow for ion transport of lithium or sodium throughout a battery. So combining this, we make our block copolymer or ionic block copolymer electrolyte systems. So in terms of this, this work has been carried out by Deakin and CSIRO, really looking at these ionic block copolymer electrolytes. And we've so far received really good results with this styrene and imidazolium acrylate ratio. And what we found is that we found the materials are worthwhile exploring and being patented actually, but one of the main steps is that in the commercial steps of making this, it's all controlled polymerization techniques. So we've got to look at how they're made, and actually if we're trying to move this up onto a larger scale, how can this be done more economically and fiscally? So the current system for producing these materials are using controlled raft polymerization techniques of each block. So for a diblock system, this is initially done with a styrene polymerization using thermal initiation, then followed by a precipitation step. And then once you have precipitated out your styrene raft agent, then you can then do the second step of doing the acrylate and polymerization to then form a diblock system between a styrene and a bromolyl ethyl acrylate. From here onwards, it's then we do a crystallinization step to swap the bromine for a imidazolium group and then produce that ionic chain. And then simply a salt substitution swap, swapping the bromine ion for a TFS ion, which is slightly better for the battery development, as bromide ions have a negative impact in terms of electrochemical window. So in terms of where we're looking at altering this current process is really the initial polymerization steps. So after each of these polymerization steps, I noticed we have to precipitate out our polymer before starting the next chain. So we're converting each polymer to about 40 to 50%, then washing away the excess monomer before carrying out the next step. So one of the things we're looking at is, can we streamline this? Can we keep it in situ and make it overall a batch process? So this is where the quasi-block copolymers come into it. So as opposed to their neat block counterparts, a quasi-block will have a sort of a tapered or gradient section in between your two blocks. This is driven by, generally you push an initial monomer to high conversion, so you'll still have a little bit of excess monomer in afterwards. So once the second monomer is added, then you have formed this slight gradient tapered block in the middle before forming your second block. So yeah, the reasons for looking at this is A, that reduced synthetic cost. If we can A, start by not having so many steps, not having so many precipitation steps involved, and B, then also we have a reduction in the amount of waste that we use in terms of the monomers. So the overall idea with these quasi-blocks is to still maintain some of these really promising properties that we've received with the neat co-block copolymers, while maintaining sort of a reduced synthetic cost. So the ways we're looking at doing this are one-pot polymerization techniques. So these have been quite well explored in terms of looking at asymmetric polymers. So the first option for this would just be a spontaneous process where both monomers are added into the same vessel at the same time. So this gives a really easy reproducibility, really easy to perform and react, but it's very limited in terms of the co-reactivity of the two monomers as a co-polymerization. So you're really wanting a high difference in reactivity ratio in order to achieve some kind of block-like structure. The second step to do is to do a stepwise addition process. So this could be as simple as a two-step process where you start with your first monomer, drive to high conversion, add a second monomer, or it could be added into multiple various different steps, depending on what kind of size and shape of your quasi-block or gradient block section you're wanting to achieve. A third option would be to use a forced polymerization technique. So this is where you try and control the composition profile by putting pressure of certain monomer composition into the reaction vessel at certain times to drive one monomer converting over another. However, this process does involve a large amount of monomeric waste, and so it's something we're trying to avoid. A final option would be to look at sort of a catalytic method, but one of the issues with this is we have our monomers in terms of what we're looking at, and in terms of catalytic processes, it's very narrow range of monomers that can be used. So it's quite difficult for us to then scale that into our own research. So overall, we're sort of looking more towards the spontaneous and stepwise approach. So in order to decide which of these was best, we looked at doing some co-monomer reactivity experiments between our two monomers, styrene and bromol ethyl acrylate. So this was just done as a series of simple NMR experiments where we trialed the conversions of the two monomers over a given time period and just measured their conversion for different compositions. So we just used a radical initiator for this process, and each monomer was kept at the monomers overall were kept at a 200-to-1 raft agent. So if you theoretically converted 100% of your monomers, you'd have a 200 unit polymer chain of each monomer. So the results from this came through. So this was the 2-to-1 ratio. So what we see is a fairly even in terms of the mole fraction of each monomer is kept fairly similar throughout the whole reaction polymerization time. So this is what's showing is that actually we're seeing that styrene is actually being uptaken a bit quicker into the polymer as it's slightly a higher composition. So we're seeing a higher uptake, and so therefore the mole fractions remaining the same. So as we reduce off the styrene content, we're actually seeing that the styrene mole fraction is dropping in the reaction material. So what this means is styrene is being more favorably uptaken into the polymer. As we do this further, this effect is only amplified. Even though now the acrylate's in a excess compared to the styrene, we're still seeing a favorable uptake of the styrene. So showing that there might be some kind of thermal stability or at least thermodynamically favorability towards the styrene, preferentially forming a radical over the ethyl acrylate. And then for the final conversion at our 1-to-3 composition of styrene to ethyl acrylate, what we actually saw was a full conversion of styrene, sort of close to 100% after 7.5 hours. So therefore, what we would have seen afterwards was just this acrylate block forming. So overall, from these results, what we see is actually we've got a difference in reactivity ratio. Obviously, styrene's showing a favorable reactivity as a copolymer. But actually what we're not seeing, we're not really seeing any kind of block structure apart from that final composition. And even so, the first part of that is still probably a random mixture rather than any kind of block structure. So from these results, what we looked at going is that we're going to look at a stepwise approach. And one of the things we're going to do is use styrene first in this, because we clearly could see that if we had some leftover monomer in styrene, then as we added the ethyl acrylate, we should see a positive reinforcement of the conversion of the rest of the styrene before the acrylate blocks form. So in terms of where we're looking towards that, we're looking at probing a few different reaction parameters in terms of these quasi-block synthesis strategies. One of these will be through reaction time monomer conversion. So probably initially we'll try and drive monomer conversion as high as possible and reduce the size of this gradient section. And then as we progress, we might increase this gradient section to see actually how a tapered block section affects the overall performance as a polymer and in terms of its self-assembly properties, but also in terms of its properties as an electrolyte. Otherwise, we're looking at solvent dilution in terms of keeping viscosity constant, obviously, if we're aiming to high conversion. And we'll also look at different initiation mechanisms. So the acrylate can also be initiated by light as well. So we might look at actually sort of having a selective thermal initiation initially of styrene and then followed by a light initiation of acrylate. So after this, we'll then characterize these polymers in terms of how controlled they are in terms of the dye blocks, their glass transition temperatures, whether we're still seeing two separate TGs for each phase, and actually the self-assembly property to see whether we can still see ordered structures. And then finally from this, we'll then produce electrolyte structures to then monitor how these are compared in terms of ionic conductivity, their mechanical performance, and overall battery cycling of these quasi-blocks as compared to their neat block counterparts. Thank you all for listening, and thank you for the RACI and all of those for allowing me to present today, and finally to all my supervisory team at both at Deakin and at CSIRO. I'm happy to take any questions.
Thank you so much, Greg. I think that that's a really interesting project, merging polymers with application, and I really think it's going to have some interesting results. We're gonna skip the questions just so we can keep on time.
No worries.
But as I said for the previous speaker, if you're interested in asking Greg some questions, then or finding out how his work is going, then feel free to email him. I'm sure he'll be happy to have a chat with you. All right, so our next speaker is Sarah Kermaniyan, and she's from the University of Melbourne. So Sarah, if you could start sharing your presentation. Brilliant. Okay, feel free to start whenever you're.
Hi everyone, thanks Georgie for the introduction. And yeah, I'm going to talk about one of my projects in my PhD. I've been working on a swellable pH responsive polymeric nanoparticles, their design, synthesis, and biological application. We need these particles to deliver drug into a disease cell through endocytosis pathway. Endocytosis process involves internalization of particle into an endocytic vesicle, fusion into the early endosome, and maturation in the late endosome, eventually degradation in the lysosome. During the maturation, pH decreases from a physiological pH of 7.4 in the bloodstream down to pH 6.3 in the early endosome, 5.5 in the late endosome, and about 5 in the lysosome. The ability of nanoparticle to induce trafficking out of acidic endolysosomal compartments without causing any cytotoxicity is one of the bottlenecks in this field. The most common endosomal escape mechanism is membrane destabilization. And you can find many papers in this regard. In this mechanism, particles disassemble into unimers, resulting in an increase in osmotic pressure and eventually the rupture of membrane. But there is another mechanism which is called particle swelling, and works based on mechanical strain. This mechanism is really poorly studied. One of the Irvine group, the second reference, they worked on this mechanism, if you are interested in looking at that. Nanoparticles in this project were synthesized using emulsion polymerization. Monomers, water-soluble initiator, and stabilizer were using emulsion media. Particles, the foreign particles in emulsion are prevented from coagulating with each other because they are surrounded with a hairy layer of stabilizers. Why am I doing this project? As I said, achieving the endosomal escape is a bottleneck, and the endosomal escape through swelling mechanism is still unclear. So to understand the endosomal escape through swelling, pH-induced swelling, we decided to make this particle. To get swelling, pH-induced swelling, we need pH-responsive monomers like DPA and DEA. These monomers are hydrophobic at pH 7.4. They become protonated and hydrophilic when pH decreases down to less than their pKa, which are 6.4 and 7 respectively. To synthesize this nanoparticle, first we need some stabilizer to use in emulsion media. So a stabilizer, amphiphilic stabilizers with 45 MPEG units as a hydrophilic block and 10 butyl acrylate unit as hydrophobic block were synthesized using raft polymerization. Then this stabilizer were used in emulsion media to make the pH responsive core using DPA, DEA pH responsive monomer, PEGMA, and a dimethacrylate monomer for labeled particles. The initial particles were synthesized based on DPA pH responsive monomer and PEGMA. In DLS, on the left side, particles were incubated at different pH from 7.4 down to 5 at 37 degrees. Then their diameter and polydispersity were measured using DLS. Polydispersity is lower than 0.2, and they swelled about 150%, but with the decrease in pH from 7.4 down to 5. Then their swelling was confirmed by a nanocyte on the right side and cryo-TEM images. In biological assays, cytotoxicity assay was performed to prove particles are not toxic for cells. Then even at high temperature, at high concentration of 50 times 10 to 9. And their hemoglobin assay was done to prove there is no polymer leakage and there is no association with red blood cells. Then a calcine assay was used to study endosomal escape. Calcine is a membrane impermeable fluorophore that is used as a model drug and a tracer to monitor the stability of endosome following particle uptake. In the control image, cells were incubated with only calcine, and a punctuate distribution of calcine around cells is indicative of endolysosomal compartmentalization of dye. The left image is for cells incubated with particles and cells and calcine. For endosomal escape, we expect to see fluorophore throughout the nucleus and cytosol. But in my case, cells are stressed and they have round shape instead of straight shape. There are two possibilities. The problem can come from the interaction between particles and calcine, or the properties of particles are not suitable for cells. So we decided to label our particle to track them in the cell membrane to see what's going on. So in the next step, labeled particles were synthesized using DPA and DEA pH-responsive monomers, PEGMA, and one dimethacrylate monomer, cyanine 5-methacrylate monomer. 3 particles with different ratios between DPA and DEA were synthesized, 1 DPA, 2 DEA, 2 DPA, 1 DEA, and the last one, 3 DPA, no DEA. DLS results show there are 140, 160, 180% swelling at pH 6, 5.8, and 5.6 as DPA increases. Then flow cytometry was used to study the interaction of particles with cells. In flow cytometry, the gray background, the gray histogram is for untreated cells with no fluorophore. The colored histograms are for cells, treated cells with a particle at different concentration of 5, 10, 20, and 50 times 10 to 9. You can see at the higher concentration, we see more association. So more concentration, we see more association. Then this data was normalized to Psi5 intensity of particle. And you can see as DPA increases, association increases. So more DPA, we have more association. Next week, I'm going to do a calcine assay to study the endosomal escape. And of course, at the same time, I'm going to make some charge stabilizer to improve the interaction between particles with cells. In conclusion, some amphiphilic stabilizers were synthesized by raft polymerization, and pH-responsive nanoparticles were synthesized in emulsion medium using amphiphilic stabilizers, and the bizarre contrast of biological assays, cytotoxicity, and calcine assays was observed. Then dye-labeled particles were synthesized and showed particles have association with cells. And charge stabilizers are going to be synthesized to increase the interaction of particles with cells. And thank you all for listening. Thanks to my supervisor, Georgina Sach, and her dad, Chris Sach, worked years on emulsion polymerization in Julax. Angus Jonathan and Moore Chen for biological assays from MIPS, and some for cryo images.
Okay,
there is a question. No problem.
Thank you, Sarah. I see that you're about to do my job for me, so that's good. Okay, so we do have a little bit of time for a question, so thank you for keeping us on time. So the questioner asks, which cells were used for the cytotoxicity and transport assays? What size of particles could be transported through this polymer?
Yes, we used the T3 cells and the DC 2.4 cells for cytotoxicity and calcineurin assays. Sorry, what was the next question? The size of particles.
Yep.
Sorry, the size of particles.
Go on to me now. Oh, hang on.
Oh, sorry, I can read them here.
Yeah.
Okay.
What size of particles could be transported through this polymer? I think maybe what size of particles can you design through this polymer?
Okay. Yeah, we can design. At the moment, our particles are in about 80 nanometer to 100 nanometer, but we expect to have smaller particles if we have a charge stabilizer. Yeah.
Cool. Okay. If there's no, hang on. Oh, okay. There's another question. Will you also study the behavior of those particles loading with APIs? I don't actually know what you mean by APIs. Do you, Sarah?
I'm not sure what API is.
But I mean, you can talk about, can you potentially study it with loading?
Yeah, of course, we can do that. It's just, of course, because we have a hydrophobic core, we can just load hydrophobic drugs, and of course for hydrophilic drugs, and we can use some linkers to load our particle with that. Just emulsion polymerization is a good method for this stuff. Yeah, of course we can.
Okay, maybe one last question. You presented the cytotoxicity data based on the number of particles per mil. Can you convert it to mgs per mil to make it consistent with other common studies in the area?
Particles per mil, we can do that, meg per mil. Yeah, we can do that, of course.
Okay. All right. Well, thank you, Sarah.
Thank you.
I really appreciate your talk, and we shall now move on to the next speaker. Okay, so the next speaker for our session is Lewis Blackman, who is a research scientist at CSIRO. Welcome, Lewis.
Hi.
Add your
can you
presentation.
see my slides okay?
I can't actually.
Oh, okay.
So
Nightmare.
if you want to do interpretive dance, then you're going to have to put your slides up.
Here we go. Oh, can you see that okay?
Yep, that's good.
Okay, brilliant. Thank you so much for having me. I'm Lewis Blackman. I'm a research scientist in biomedical manufacturing program at CSIRO down in Victoria. Until recently, I was a postdoc there. I've now moved into a new role, but I'd really like to share my research into honey-inspired antimicrobial materials with you. So I'm sure many of you are aware, but the bacterial and fungal threats that we face are becoming increasingly resistant towards our sort of current cohort of antibiotics that we have available to us. Antimicrobial resistant infections are actually set to overtake cancer in just 30 years' time. So by 10 million people every single year. And it's not only that the bacteria are becoming more and more resistant to our current antibiotics that we have available, we also have a decreasing pipeline in the number of new antibiotics that are approved for clinical use. So basically, we're in desperate need of finding some new solutions to address this problem. In a related sort of statement, 1 in 25 patients that come into hospital fitted with a medical device will actually end up having an infection that is related to having that device fitted and their hospital stay. So this is obviously a huge problem in the medical device industry as well. Thinking about the current pandemic that we're sort of living through, obviously COVID-19 is a viral pathogen, but there was a report that came out about the initial sort of Wuhan cluster last year, and it showed that almost all of those patients were actually treated with antibiotics when they came into the hospital, and yet 1 in 7 of those actually went on to develop a secondary infection anyway. looking at all of the non-survivors, almost half of those had a secondary infection, and of those, sepsis was the most common complication. Now, of course, we've heard about patients needing ventilators, and almost a third of those ventilated patients actually went on to develop ventilator-associated pneumonia. So again, this comes back to the issues around the use of medical devices. And so this is really just to say that there is a complex interplay between viral and bacterial threats, and this may have possible implications in the future when we're considering the rise of antimicrobial resistance and the possibility for future pandemics. So my research is really in the area of hybrid materials. And what do I really mean by that? This is where we can take a biologically derived material like LC, and they're highly specific and often not very synthetically accessible. And we can sort of formulate these up with synthetic materials like passive polymers, ones that can introduce some additional functionality or responsive behavior. And the idea is to try and design these to have a complementary functionality to the biologic, but they have the added advantage of being scalable and highly tailorable and cost effective. And when we have our biohybrid materials, the aim is to try and solve some major challenges in healthcare. And you might be asking, okay, why would you want to use biohybrid material over just a normal native biologic, let's say? And I'll use one example from my PhD as to why we'd like to actually do this. So this is asparaginase. It's a therapeutic enzyme that's used clinically in the treatment of leukemia. So it's not an antimicrobial asparagine, which these leukemia cells actually can't make, so you selectively kill those cells. And this is great, but it has a range of really nasty side effects. And the worst one is the allergic reactions and anaphylaxis. And the reason for this is, like all biologics, or particularly therapeutic proteins, it's really susceptible to proteolysis and rapid clearance in the body. And this means that you have to keep increasing the dose or the dose frequency. But when you do that, you actually risk then that protein being recognized by your innate immune system as being foreign, and that leads potentially to the anaphylaxis. And so what we developed during my PhD was we can actually encapsulate these proteins inside a polymer capsule, and that blocks the antibody recognition and the proteolysis of that protein, but you can still actually retain that function. So I'm not going to be able to have time to go into these studies there, but the references are there if you want to check that out, and I'm happy to talk about that towards the end. But when I came to CSIRO, we were thinking, okay, well, how can we actually use that technology to look at new antimicrobial materials? So we thought about thinking about really interesting material to be used, and we've actually been using it since ancient times. This is a report of honey being used as a wound dressing in a very early surgical script. And honey has a whole range of different antimicrobial mechanisms, but one of the main mechanisms that it has is an active enzyme, glucose oxidase, and this can convert the high glucose concentration to hydrogen peroxide, which is a reactive oxygen species biocide. Glucose oxidase itself is listed as a GRAS compound by the FDA, so we thought this would be a great place to start to make some antimicrobial materials. Now, the way that we make these particles is by using polymerization-induced self-assembly. If you're not familiar with this technique, this is where we can take a macro initiator or macro CTA that starts off water-soluble. You then do a chain extension in water with something that starts off miscible as a monomer, but once it polymerizes, becomes insoluble. And this actually drives the self-assembly towards these hollow capsules. And you can do this in the presence of enzymes, and you end up with random encapsulation of those enzyme species, plus a whole load of stuff in solution. So you have to then purify your protein, purify your polymerosomes out from the free protein that's floating around in solution. And you'll see that these actually survive this process. So this is done by light scattering with and without glucose oxidase. Looks fairly similar. And also by transmission electron microscopy, you can see that they have this vesicular hollow shape. So that was great. So are these still permeable like asparaginase loaded vesicles that I showed you before? And of course they are. So using colorimetric assays, we could show that when you increase the glucose concentration, you can increase the rate of hydrogen peroxide that's produced. The empty particles, of course, do nothing, even at the highest glucose concentration. So this was great. How do these actually interact with bacteria? And the way that we sort of assessed this was we took our GOX-loaded nanoreactors, we mixed them in media with some bacteria, we allowed for some growth or our polymerzomes to do their thing and kill the bacteria, and then we took that solution, made serial dilutions onto agar, and then counted how many colonies there were to work out their viability. So these are the actual agar plates that we get back from that assay, and hopefully you can see that for Staph epidermidis, this is a gram-positive bacterium. For the empty vesicles and the PBS control, you're seeing some growth there, whereas in the case of our GOX-loaded nanoreactors, we're seeing complete killing of the viability of these bacteria. Hopefully this is a little bit more clear when we look at Staph aureus, because they form larger colonies, but this is the quantified data. So we essentially have a 5-log reduction in the bacterial viability against these planktonic gram-positive bacteria. And I should say that this is just using the glucose that's already present in the media. Next, we moved on to gram-negative bacteria. These are a little bit harder to kill. So we looked at 2 escape pathogens, E. coli and Klebsiella pneumoniae. And we were a little bit disappointed when we first did this, because under those same conditions, we actually saw no activity. But of course, these are glucose responsive. So when we start adding glucose into our system, now we're starting to see some of that antimicrobial activity coming through. And these are really effective at high glucose content. So what about resistant bacteria? All of the bacteria that I showed you before was susceptible. We were fortunate enough to collaborate with UQ. He's from the Alfred Hospital, Monash University, and he had access to a clinical isolate of methicillin-resistant Staph aureus. And we repeated our assay using this strain, and hopefully you can see the GOX-loaded vesicles, as well as the free native enzyme, are really effective at killing MRSA. And this is because obviously it's resistant to methicillin, but the same the pathways that it uses to get around methicillin's mechanism of action are highly different to the broad spectrum antimicrobial that hydrogen peroxide is. So these are really effective against resistant strains as well. What about biofilms? So we've spoken about planktonic bacteria. Actually, the majority of bacteria live in these surface adhered communities that they're surrounded by this extracellular matrix that protects them from antibiotics from getting in and killing those. I just want to highlight here, we've actually had a ChemSoc Rev article that I'm super proud of, obviously written last year during lockdown, but we've just got to the inside front cover of ChemSoc Rev in an upcoming article where we're reviewing antibiofilm peptides, proteins, polymers, and biohybrid materials as well. So please go and check that out. But back to our original study, UQ managed to grow up these MRSA biofilms, and we wanted to test the efficacy of our nanoreactors against the biofilm. And you can see that the nanoreactors retain their activity relative to the free native protein. But you can see that relative to when we were looking in the planktonic form, this study really highlights the difficulty of treating a biofilm once it's already been established. And that sort of brings me on to this last short project that I'll talk about, which is how do people actually resist bacteria biofilm formation on surfaces. So the current approach is for how we want to try and do this is to either have a low fouling coating that resists the coatings that are actively contact killing. So when bacteria actually sit down on that surface, they rupture the membrane, something like that. Or you can have a surface that releases a biocide, like a drug-impregnated material. And we wanted to try and combine 2 of these classes and have, let's say, a low fouling material that could also release a biocide. And this work was really performed by Tiffany Zhang. She's a really talented master's student who came to work with us from Chemie Paris Tech. And what she did was blend up glucose oxidase in solution with a difunctional PEG, which is a low fouling polymer. This forms a hydrogel when you irradiate using a photoinitiator. And the idea is that these should remain low fouling because it's got a high PEG content, but it also is not only able to release a biocide, but create its own biocide from the glucose that's around in solution. She looked at a range of different cross-linking densities, and she showed use. And she also studied using colorimetric assays, their longevity over a period of a month. And we can see that those that had the highest cross-linking density had the longest longevity because they were able to retain the enzyme inside the gel for the longest period. So this is great. They can produce hydrogen peroxide. How do they interact with bacteria? So we went back to Staph epidermidis, and we showed that these had now a 7-log reduction in the viability of Staph epidermidis in all cases. And this is after a 5-day sort of soaking period. But more importantly, they also kept their low fouling properties, even in the case of the empty hydrogels. So in the case where you have the glucose oxidase loaded hydrogels, you consider you're having this synergistic effect of the hydrogen peroxide production, which is the antimicrobial aspect, as well as the passive PEG diacrylate low fouling properties. So finally, I just want to conclude. So I hope I've convinced you that by using biohybrid materials, you can increase or improve the functionality and performance of biologic materials. We then applied this to an antimicrobial enzyme that was present in honey to create some new antimicrobial materials. These were effective in planktonic form against gram-positive and gram-negative bacteria, including resistant strains. They retain their functionality against biofilms, and we were also able to use these enzymes to form hydrogels that had both low fouling and antimicrobial properties. Finally, I just want to thank everyone that was involved in my postdoc, Catherine Locock and Peter Cass, who were my supervisors during that period, UQ at Monash, Zeu, who carried out some cytotoxicity for us, especially Tiffany Zhang, who did the student work, as well as all of those people that were involved in my PhD project that I mentioned there at the beginning. I just want to thank everyone, and thank you for listening.
Brilliant. Thank you so much, Lewis. Once again, as usual, another brilliant talk and such interesting materials. So we do have a time for a quick question. So the first one was, is this technique compatible with conventional acrylic coating formulations?
Sorry, I'm not exactly sure what the question's asking. Do you mean that could you? I'm actually not sure which technology you're talking about. You're talking about the nanoparticles, the gels. I guess if you're talking about the nanoparticles, yes, it's possible to blend these up into an acrylic sort of coating formulation. We've actually tried something similar to that, but it's more to do with, I guess, how long does an enzyme actually survive when you've dried it down onto a surface at room temperature, and how useful is that? So I think there are some things that you can certainly do, but I guess the main advantage of this biohybrid system is that you are reducing the proteolysis, you reduce the immunogenicity, so you hide the protein from your body, and you also hide your body from the protein, I guess. And the other thing as well is that now we have a platform for introducing additional functionality. So, you know, you can think about targeting or imaging.
Brilliant. Well, I think we're going to leave it there so that we stay on time, but I just draw your attention to Lisa's question. See how fun the polymer community is? Maybe next time you can tie it as an interpretive dance, Lewis. Okay, so thank you again, Lewis, and we'll move on to our next speaker. Okay, so our next speaker is Nam Dao, who is from a PhD student from Monash University. Welcome, Nam. Do we have Nam? Yep. Nam, you're going to have to come off mute. Brilliant.
Okay. Okay, thanks, Georgie, and hi everyone, and welcome to my presentation. So in today's presentation, I would like to present about trisulfide-bearing polymers to arrest cellular oxidative stress as a means of cytoprotection. So when we talk about protection, we can think about someone with a shield or a sword, or someone in the time of COVID-19 pandemic with a mask, or someone who is vaccinated. Similarly, cytoprotection can be referred to the compound which can protect the cells from being toxic by the toxins. For instance, those can reduce the side effects of the anti-cancer therapies as a normal disease, or those which can recover the function of cells after being damaged by the injury, for instance, in the brain ischemia or heart ischemia. And different cytoprotective agents have various working mechanisms. For instance, they can decrease the level of inflammatory, they can restore the mitochondrial functions, or they can alleviate oxidative stress by reducing the level of reactive oxygen species. And interestingly, in our kitchen, we can find one compound, one product, which is known to be one cytoprotective compound. That is garlic. So garlic is known to be a good source of hydrogen sulfide and pearl sulfide. And those compounds, they play vital roles in the biological activities. Let's have a look closer in one derivative of the garlic extract, namely dilute trisulfide. So in the structure here, we can see that the trisulfide bridge in the structure of dilute trisulfide, and the bridge can be broken down to release one hydrogen sulfide molecule, and also other pearl sulfide compound. And hydrogen sulfide and pearl sulfide, they are known to be strong antioxidants, which can scavenge different reactive oxygen species. And importantly, those compounds can help to rescue the functions of the proteins which are damaged by the oxidative stress. Motivated by the garlic extract, in our research group, Dr. Francesca has well investigated the trisulfide chemistry. And to us, there's one compound which is very promising, the compound named T. So T has a peg chain, a trisulfide moiety, and then a cresol moiety. Similar to the dilute trisulfide, T was shown to exhibit the cytoprotective effect, which includes the stabilization of the cellular membranes, the ability in reducing reactive oxygen species levels, and the ability in rescuing cells from being toxic. From that result, we were wondering whether the compound T can have any effect on cancer model. And to answer the question, we have employed one co-culture models in which we co-culture normal and healthy fibroblasts and breast cancer cells. And we want to see whether in the co-culture condition, the T1 can exhibit any ability in manipulating the cell functions. So the first result and the most important finding to us is the changes in the reactive oxygen species levels in the co-culture cells. In the middle image here, these are the co-culture cells, which include the fibroblasts and the breast cancer cell. The breast cancer cells, they have higher intensity here. That means the cancer cells under the co-culture condition, they can produce a huge amount of ROS compared to the surrounding fibroblasts, and also higher than those from the monoculture cancer cells. Other cellular functions that we observed under the co-culture conditions is the changes in the collagen 1 produced by the fibroblasts. So under the co-culture condition, the cancer cells, they force the fibroblasts to produce the collagen 1, and collagen 1 is necessary for the cancer progression. And that can be seen here that the level of the collagen 1 produced by the co-cultured fibroblasts, which is in red color here, is higher than those from the monoculture and healthy fibroblasts. And we also can see the changes in the actin density of the co-culture cells in comparison with those from monoculture fibroblasts or breast cancer cells. And the changes in the reactive oxygen species, change in the collagen 1 and change in the actin density are also reported in the tumor microenvironment. That means the co-culture that we developed here can simulate the interaction between the cancer cells and the surrounding counterparts in the tumor microenvironment. So when we applied the donor T to the co-culture system, we found a significant reduction in the reactive oxygen species levels in the co-culture cells, which include co-culture fibroblasts and co-culture cancer cells. And importantly, the effect from T was shown to be better than those from positive controls or other antioxidants such as N-acetyl-cysteine or glutathione. That means T1 is a very good antioxidant. We also look at the changes in other cellular functions, and specifically, we look at the collagen 1 in the co-culture fibroblast. So as mentioned, under the co-culture conditions, the cancer cells, they force the fibroblasts to produce more collagen 1 for their progression. And treatment with the T compound can reduce the ROS of the co-culture cells. And now T1 can also downregulate the level of collagen 1 produced by the fibroblasts under the co-culture experiment, while the T1 has less impact on the monoculture healthy cell fibroblasts. That means T somehow can have selective inhibitory effect on the fibroblasts, which are impaired by the cancer cells. So to sum up, in this project, we demonstrate a co-culture model to simulate the interaction in the tumor microenvironment and the ability of using the trisulfide donor to alleviate the cellular functions. So with the result, we were motivated to see whether we can improve the trisulfide loading capacity into the polymer structure. So instead of one, we want to have more than that. And to this end, we have designed the trisulfide brass polymers and challenged the ability in arresting oxidative stress as I am presenting now. So first, we report two monomers with the trisulfide located on different positions compared to the double bond, M1 and M2. And then we use a raft polymerization to co-polymerize the trisulfide monomer with plasma to form a series of polymer with different trisulfide densities and trisulfide locations. And 7 polymers have been made, including M0 without any trisulfide equivalent. And all the trisulfide monomers and all the polymers have been made here. They have a narrow and similar molecular weight distribution. We can carry up to 4 trisulfide equivalents. And interestingly, they are all well tolerated by the head cells. So in order to evaluate the H2S releasing ability of the macromolecules, we have employed 2 techniques. In the first technique, we use an amperometric probe. And we use glutathione to trigger H2S release. As can be seen from 2 graphs here, the polymers from M1 base monomer and M2 base monomer, they all release H2S and show the good releasing profiles. And the ability of releasing releasing H2S correlates with the percentage of the trisulfide monomer in the polymer structure. For instance, M230 here stands for the polymer with 30% of M2 monomer in the polymer structure. In the second technique, we use a fluorescent chemical probe SF4. The probe can react with iron sulfide and turn into green fluorescence. And in this experiment, we test 2 polymers, M130 and M230, both 30% of the reactive monomer. And the two polymers can all deliver H2S intracellularly, as can be seen from the SF4 channel here. So when the trisulfide bridge is broken down, it will release iron sulfide and also pearl sulfide. And all those molecules are known to be antioxidants. And as such, we evaluate the ROS alleviating ability of the macromolecular. And in this experiment, we use an external source of reactive oxygen species, namely iron peroxide. So when we treat the cells with the iron peroxide, the ROS level was elevated compared to those without any treatment. Interestingly, when we treat the polymer before adding the H2O2, the polymers can help in maintaining the ROS level at baseline values in comparison with the group without any treatment. That means the polymers M130 and M230 can alleviate an external oxidative stress. So in this project, we demonstrate the ability of making a brass polymer with different trisulfide location, different trisulfide density. So to conclude, in this true project, we demonstrate that trisulfides are a good source of sulfur-based cytooperative agents, which include iron sulfide and the pearl sulfide compounds. And linear and brass polymer can be made to carry trisulfide for various functions and applications. And finally, I would like to acknowledge all my supervisors, Dr. John Quinn, Dr. Michael Whittaker, and Associate Professor Erica Slot, and all the people in the project and all the funding to support my research and my study in Australia. Thanks for your attention.
Thanks, Nam. Very interesting project, and we've seen this starting to emerge over a number of years now, so you're really getting a body of work in this area. Let me look. We do have a couple of minutes for questions. I have a question to start people off, and it's probably not a surprising question for me. I'm interested, so where in the cell, once they get inside the cell, where do these materials go? Do they get trapped in endosomes, or do they go across membranes, or what happens to them? Okay, we didn't really look at the trafficking of the polymer inside the cells, but when we look at the SF4 channel here, we can see that it's pretty punky, and we thought that the polymer end up in the lysosome. Okay, interesting. Thank you so much. Thanks. Okay, so we still do have a few minute or two if there's a burning question that someone wants to ask. If not, we will continue on, and we will be early, which is incredibly exciting. So thanks again, Nam, for your great talk. And yeah, let's move on to the next, and I think final speaker for our session. No, I think we have two more. The first one is Glenn Clothier, and he's a PhD candidate from the University of New South Wales.
Hello, is this working?
I can definitely hear you.
Okay.
So that's your presentation, and yeah, there it is. Good.
Right, sounds good. Okay. Right, so I guess I'll begin. So hello everyone, my name is Glenn Clothier, and today I'll be talking to you about multi-block copolymers and radical penetration in dispersed systems. So before I delve into the complexities of multi-blocks, I think it's important for me to actually explain what something called RDIP is, reversible deactivation radical polymerization. So basically this is a technique to keep the ends of your polymer chains living. With a conventional polymerization, of course, you have termination at the end of your reaction, but with RDIP techniques, you can actually keep the ends living, so you can post-functionalize or chain extend more blocks after the fact of the reaction. So there's a number of methods used in RDIP, the main ones being NMP, ATRP, and RAFT, reversible addition fragmentation chain transfer polymerization, which is the one that we're focusing on today. So ATRP and RAFT are commonly used to make multi-block copolymers. So how this basically happens is that you have your first block, and if it's mediated by, for example, RAFT or ATRP, it will retain its living characteristic at the end of the reaction. And so you can chain extend more polymer, and so on and so forth, each retaining the living characteristic at the end. So why do we ever want to do this? As you can see, there's a number of applications I've got up here, but the main allure of multi-block copolymers is that you can actually combine a bunch of different polymers together and combine their properties, since the final polymer will combine the properties of the constituents, and you can sort of edit this depending on which one to use and how long they are to whatever you really want to do. Unfortunately, there are a number of limitations associated with multi-block copolymer synthesis. Some of the most pressing ones include conversion. Unless you want a quasi-block copolymer, which is the goal of some methodologies, you do need full conversion for each block, lest you have contamination of previous monomer in future blocks. And if you don't have full conversion, then you need extensive and laborious purification steps for each block. The reaction time for RDIP syntheses is usually takes a longer time than conventional radical polymerization. So that's another issue to be aware of. The dispersity of your polymers has to be quite low. So basically all of your polymers have to try and grow at the same length. It's often difficult to access high molecular weights with these sorts of syntheses. And finally, you can face issues with compatibility between monomers with each other, or with like raft agents with different monomers as well. So a number of these limitations were overcome relatively recently, 2011. There was a strategy using a type of ATRP which allowed for high conversion and high livingness in a relatively short amount of time. And soon after, a similar thing was done with RAFT with good shifting, as you can see with these chromatograms. So today, as I mentioned before, we'll be focusing on RAFT for our multi-block syntheses. The main reasons being that there's good robustness conditions, including temperature and also oxygen content. is compatible with a wider range of monomers than a lot of other RDRP syntheses. And also it can be able to mediate a number of different techniques, including dispersed polymerization, in our case, emulsion polymerization. So speaking on emulsion polymerization, why are we doing this? Well, we have we look here, we've got an homogeneous polymerization systems. This can be solution of bulk. With these sort of systems, since your propagating radicals are homogeneously distributed, they have access to each other. So they actually sort of wham into each other and terminate. And for living polymerization, this is not what we want, obviously. Termination means we can't chain extend anything on the end of it. But with emulsion polymerization and some other dispersed systems, our propagating radicals are sort of, they're segregated into these nanoreactors or micelles, if you will, and actually removes all the termination. They're actually hindered from actually accessing each other and bimolecularly terminating. So this has a number of consequences. Firstly, the lower termination instance enables you to lower the reaction time. You also have a higher living character for your polymers, enables you to access high molecular weights, and also increase the amount of usable practical monomers you can actually synthesize, or polymers you can synthesize. For example, low Kp monomers like methacrylates, you can actually polymerize them in good time using emulsion polymerization. There's a number of other benefits as well. The continuous phase is water, so it's environmentally friendly compared to a solution polymerization. Emulsion polymerization is common in industry, and also the product is quite convenient for things like lacquers, coatings, and adhesives. So now I'll talk a bit more about our specific strategy in multiblock syntheses. So usually we've got our raft agent, and onto this we polymerize polymethacrylic acid, which is hydrophilic, and polymethyl methacrylate, which is hydrophobic. When we do this, we actually synthesize an amphiphilic macro raft with a hydrophilic and hydrophobic section. So with our emulsion polymerization, this negates the need of an extra surfactant. The surfactant is the raft agent itself. And so once we have these aggregates in the water, we can introduce a monomer, in our case, usually N-butyl methacrylate, and this will go and via emulsion polymerization mediated by raft, create a seed latex. Now from this seed latex, we can introduce another monomer, let's say monomer A, once it reaches full conversion, then we add monomer B, full conversion, monomer C, full conversion, and then we'll have a polymer particle in the end. Should be noted that usually our R group is anchored on the surface, and so there's a high concentration of Z group around the center. And if we have a propagating radical, this has to reach the center to be mediated by raft, which will be important later on in my talk. Okay, so now I'm on to my specific methodology. So what I set out to find was to see how two main parameters, local monomer concentration within polymer particles and polymer TG affected the final polymer quality. So for example, like molecular weight distribution and dispersity. So in terms of monomer concentration, we've got two sort of strategies here. Firstly, we have our seed latex, and from this, a chain extended 10 blocks, which each block has a degree of polymerization of 100. And we also have a seed latex here. We did another polymerization where we have 2 blocks where each DP is 500. So the final polymer is the same length, and also we have the same polymer used for each of these. However, because the different block numbers and the block DPs, the monomer concentration in DP equals 500 system ends up being significantly larger throughout the reaction than that of the DP 100 system. And the three polymers we used monomers, should I say, are N-butyl methacrylate, isobutyl methacrylate, and tert-butyl methacrylate. They're all isomers of each other, but with very different TGs, range from 20 all the way to 117 degrees Celsius. Okay, so now onto the results. So with our low TG polymer, poly N-butyl methacrylate, when we've got the results for the DP100 and DP500 systems. With the DP500 systems, your chromatograms, the molecular weight distribution is actually slightly narrower than that of the DP100 system, but not to a significant extent. However, when we did the exact same polymerizations with a high TG polymer, 117 degrees, then we do have quite a stark difference. With our block DP equals 100, we've got a bimodal distribution, implying there's some polymer here which is not under raft control, and a very broad distribution in general. And also it stops shifting around the fourth block. While with our DP 500, while by no means perfect, its molecular weight distribution is much less broad than that of its DP 100 counterpart. So why is this the case? Well, to do this, I have to introduce the concept of radical penetration. So let's say we've got a low TG polymer particle here. So with emulsion polymerization, I'm sure many of you know this, but we actually we have our initiator dissolved in the aqueous phase, and then it will polymerize a number of units until it becomes too hydrophobic. And then after that, it will actually enter the polymer particles. If your polymer has a low TG, it's going to be relatively soft, and therefore radical penetration won't actually be hindered. It's actually going to diffuse quite easily through to be mediated by the raft groups near the center. However, with a more high TG polymer, our polymer particle is the same, except it's quite a lot harder. So when you have your ZMA introduced into the system, it actually has a much slower diffusion rate because this hard polymer. And therefore, there's a much higher probability that your ZMA will actually terminate before it reaches the raft moiety in the center. So this termination events and uncontrolled polymerization is what we believe that these sorts of the wide distributions in the bimodal peaks are. And I guess we should also mention how the monomer concentration plays into this. The DP100 systems are usually worse than that of the DP500 systems in terms of molecular weight distribution. We believe this is all to do with radical penetration. Higher monomer concentration throughout the reaction within these particles will act to soften the particles. And softer particles, of course, mean that you have greater ability for propagating radicals to diffuse through the polymer particle, leading to actual more high degree of raft mediation and lower distributions. So we did a sort of a proof of concept with this. Along with the N-butyl methacrylate and the tert-butyl methacrylate, we have the intermediate isobutyl methacrylate with its TG of 57 degrees. And indeed, it would have an intermediate degree of radical penetration between its two counterparts. And as you can see, the molecular weight distribution is broader than that of the soft poly N-butyl methacrylate, but much less broad than that of the high TG poly tert-butyl methacrylate. Also, we have here, we did a repetition of our poly-tert-butyl methacrylate experiment with the DP100, but with each block having a 25% weight, mass weight toluene, and it's the exact same reaction but with toluene, and this would act as a plasticizer to soften the particles, again, similarly acting like the monomer. And indeed, our molecular weight distributions are a whole lot less broad, and also the bimodal peak is gone, implying that the radical penetration enhancement due to the softening of the toluene actually gave us a better result. So we decided that we could exploit this and try to and see if we could actually polymerize high TG polymers or high TG monomers, and actually be successful in creating a good molecular weight distribution and good shifting. So we decided we could try using organic initiators to achieve this, which aren't generally used in emulsion polymerizations. So with a hydrophilic initiator, I've already briefly gone through how this works, but I'll just go through it again. You polymerize a few of the monomer dissolved in the aqueous phase until a critical length is reached, and this ZMA will become hydrophobic, enter a polymer particle, and if that polymer particle is too hard with a high TG, then it won't be able to diffuse towards the raft agent in the center before terminating. However, with an organic initiator, this is actually soluble within the polymer particle. So this would start within it instead of outside. And so when your thermal decomposition occurs, what actually happens is that quite often radical exit can happen. And so one radical will exit the polymer particle, and then this remaining radical fragment can actually have a shorter distance to travel to the raft moiety around the center. It doesn't have to penetrate the surface. And also it's much more compatible with this polymer than its hydrophilic counterpart. So its diffusion coefficient will be much greater. So it's much easier for this to actually be able to be controlled by raft. It should also be noted that occasionally what can happen is that when you have your decomposition, the two radicals can terminate via the cage effect. And this can, I guess, happen instead of the radical exit. Though in our case, it's been demonstrated before that radical exit is actually competitive with the cage effect. And it actually doesn't happen to that large an extent if your polymer particles are large enough, which is in our case, they are. And also our conversion is still quite high, sort of implying that much of this didn't particularly, there was a decent amount of it, but not a huge amount, not enough to significantly affect our system. Okay, so now on to the results of this. So we tested 4 different initiators of varying water solubilities, KPS, ACPA, AIBN, and BPO, in order of decreasing water solubility. So once again, our results are quite stark. Our KPS system, we have our bimodal distribution, as you saw before, stopping shifting around the 4th block, and it's quite a broad distribution in general. But as your initiator becomes more hydrophobic, your shoulders start to disappear, your molecular weight distribution starts to narrow, and your shifting actually stops later until you have the BPO system where shifting happens all the way up to the final block, and we have quite narrow distributions, even with this high TG polymer. So we believe what's happening is that, as I explained before, the radical diffusion through the polymer is much enhanced with the BPO system. And of course, as you get more hydrophobic with your initiator, your diffusion will get better through the polymer since it's much more compatible with it, as opposed to a hydrophilic KPS. Yeah, so we decided to do another proof of concept with this. We decided to polymerize a multi-constitutional heptablock consisting of 7 different methacrylates, each with DP100, and see how this would go in comparison to BPO and KPS. So even though the polymer TGs of our constituent methacrylates weren't incredibly high, we still saw quite a marked difference in our chromatograms. The BPO is narrower than that of KPS, and our dispersities of the BPO system are also lower as well. So yeah, in conclusion, our strategy was successful in determining the significance of radical penetration. We did this with scalable polymerization, low Kp monomers, and we're able to polymerize both high and low TG polymers with multi-blocks using organic initiators. Thank you.
Thank you, Glenn. Another really great presentation. We do have a couple of moments for a question. So we have one, and that is, what is the driving force of radical exit?
Driving force of radical exit. This is a pretty complicated question. Yeah, so it can be a few things. A lot of the radicals, according to a paper which I read, they sort of can originate in the surface, and it seems sort of counterintuitive that organic radical can actually exit a particle into the water phase. But apparently what happens, or more specifics of this radical exit, is that initiators closer to the surface of the particle can actually interact with water and create a hydroxyl radical instead of the actual organic initiator radical. And that, of course, is much more hydrophilic and can exit the particle. However, I guess the specifics of this aren't too well understood as far as I know, considering there's not too much work in organic initiators in emulsion polymerizations. But from what I've read, that is basically what happens.
Okay, thanks, Glenn. You've obviously had a look into that, so that's a really interesting answer. Okay, so I think, okay, one last question. The hydrophobic initiator will generate radicals inside the particle, right?
Yes.
Yep.
Yep.
Okay, good. Well, that was a nice straightforward answer to finish us off. Okay, thank you, Glenn, for your presentation. We really appreciate it. And our last presenter for this session is Gayathri Ediriweera, who's a postdoctoral fellow at the University of Queensland. Okay. Thank you. Okay.
Hello, can you hear me okay?
We can totally hear you. Brilliant. Thank you. Please
go. Gina. Oh, good. So, hi everyone. I'm Gayathri Ediriweera, a postdoc from Chris Thuret's lab at UQ. And yeah, this is my first postdoc project that we started mid last year in collaboration with the University of Wollongong. Yeah, I think before starting this, I should give you all a small heads up. So this project involves a lot of biology than polymer chemistry, but most of that biology wouldn't have been possible if it was not for the polymeric material. So I hope you will find it useful. Anyway, so the project is about developing a nanoparticle-based drug delivery system for the treatment of motor neuron disease. And for those of you who haven't heard what is motor neuron disease, it's actually a collective term for a group of progressive neurological disorders that degenerate the motor neurons in our body. Those are the cells that are responsible for our normal skeletal muscle activities like walking, breathing, swallowing, etc. And there are many different types for motor neuron disease, but more than 90% of the cases fall under the category of this amyotrophic lateral sclerosis or ALS. So most of the time when people say motor neuron disease, they are actually referring to ALS and vice versa. So in a healthy person, what usually happens is signals from the motor cortex of the brain will get transmitted to brainstem and then to spinal cord through upper motor neurons, and then from the spinal cord to muscles through lower motor neurons. And that's how we move our muscles and do all the day-to-day activities. But when a person is suffering from ALS, for some reason, the lower motor neurons can't receive signals from the upper motor neurons. So the muscles are not getting any signals, and over time they will become weak. This will slow down the voluntary movements and it will ultimately lead to paralysis. And this ALS is mainly divided into two types. One is familial, where the disease occurred due to genetic reasons. And the other one is sporadic, where the reason for disease can be anything like age, environmental factors, etc. And after the onset of symptoms, usually the average life expectancy is limited to 3 to 5 years. And unfortunately, there is no perfect treatment yet. So it can't be cured. The only possibility is to extend the survival. There is one FDA-approved drug for worldwide use for ALS called Riluzole. And there are some other clinical trials going on with agents like copper ATSM and antisense oligonucleotides, even in Australia. So hopefully we'll hear some good news from these in the near future. So as I said earlier, ALS is divided into two types. One is sporadic, where the reason for disease can be anything. The other one is familial. So 5 to 10% of the ALS cases occur due to genetic mutations. The exact reason for these genetic mutations to occur is not fully understood, but scientists believe protein misfolding and aggregation in motor neurons to be one of the most important factors contributing to ALS. And so far, several genes have been discovered like this, whose mutations have been found to cause ALS. But the one that we are interested in is called as superoxide dismutase 1 or SOD1. So this was the first gene that was discovered back in 1993, whose mutations have been found to cause ALS. And the SOD1 protein made out of this gene is responsible for the catalysis of harmful superoxide radicals into hydrogen peroxide and oxygen in cells. So when we think about this SOD1 related ALS pathology, the abnormal accumulation of this mutant SOD1 in motor neurons is one of the hallmarks. So if we can reduce this mutant SOD1 in motor neurons, we should be able to control the disease. And that's what scientists thought. So many studies have been dedicated to that. And one of the most promising candidates who can do that is called antisense oligonucleotides. They are like this short synthetic single-stranded oligonucleotides, mostly DNA. They can alter RNA and modify the protein expression in cells. There are several mechanisms through which antisense oligonucleotides can do that, but the one that we are interested in is something like this. So we will have this antisense oligonucleotide developed against the mRNA responsible for the SOD1 production. So when we administer that oligonucleotide, it will go and bind to that mRNA through Watson-Crick base pairing. And this DNA-RNA hybridization will activate the RNase H enzyme in cells, which will go and splice that mRNA, and it will reduce the protein production. So a few of these antisense oligonucleotides are already in clinical trials as well. So they are very promising candidates. Yeah, but of course there is some problem as well. The problem with antisense oligonucleotides is that it can't cross the blood-brain barrier by itself to reach the central nervous system. So most of the studies involving antisense oligonucleotide, they involve like direct intraventricular or intrathecal injections that can result in harmful side effects, especially when repeated injections are needed. So this emphasizes the need for alternative delivery platforms to deliver these antisense oligonucleotides into the central nervous system. And yeah, as people working in the nanomedicine field, the first thing that's coming to our head is then why not use nanoparticles? So that's the case. We developed these calcium phosphate lipid nanoparticles that can deliver antisense oligonucleotides into the central nervous system. Why calcium phosphate? Because they have been used for plasmid DNA delivery for decades. They are biodegradable, and also they have a good stability without a lipid coating, and they have a smaller enough size that can help in crossing the blood-brain barrier. And the most important thing here is that some of the phospholipids that we are using in the outer lipid coating, they are being modified with polyethylene glycol or PEG. So that will not only help by providing stealth properties and also longer in vivo circulation time, it will also facilitate the targeting agent that we are going to use. In this case, it's a bispecific antibody that can bind to the methoxy-PEG of our nanoparticles and also to the receptor that we are targeting. So in this case, it will be the transferrin receptor that is expressed in the blood-brain barrier endothelial cells and also present in neurons. So the overall idea of the project is to deliver these targeted nanoparticles into the central nervous system of mice using non-invasive systemic delivery. So we started off by synthesizing our nanoparticles. So in a very brief way, first we made the antisense oligonucleotide loaded calcium phosphate course using water in oil microemulsion method. Then we did the phospholipid and PEG coating using thin film hydration method. And the oligonucleotide that we used, it's also labeled with Cy5 dye for imaging purposes. The particles were roughly 70 nanometers in size, negatively charged. Also, the flow nanoanalyzer indicated the presence of antisense oligonucleotide in all the nanoparticles when we compared it against a non-loaded nanoparticle population. And the antisense oligonucleotide encapsulation efficiency was roughly 30%. So after thoroughly characterizing the particles, we moved on to in vitro studies. Here we used a mouse motor neuron cell line called NSC34. First, we wanted to check the cytotoxicity of our nanoparticles using MTA's assay. So as you can see here, we didn't see any significant cytotoxicity for the concentration range that we tested. Then we also checked the cellular association and uptake of nanoparticles using flow cytometry as well as confocal imaging. So as you can see here, we saw a nice dose and time dependent uptake of nanoparticles into mouse motor neuron cells. Then we also saw that our oligonucleotides loaded inside nanoparticles were actually stable in serum through agarose gel electrophoresis. And then we checked the pH dependent dissociation of nanoparticles. So if you look at the intensity here at low pH, most part of the oligonucleotides are being released from the nanoparticles compared to the normal physiological pH of 7.4. As the next step, we wanted to see whether our oligonucleotides loaded in the nanoparticles can actually reduce the SOD1 levels in human embryonic kidney cells. Why we use hex cells for this? Because the oligonucleotide that we are using is actually developed against human SOD1. So that's why we changed the cell line to this. And as you can see here from the intensity, our oligonucleotide loaded nanoparticles were actually capable in significantly reducing the SOD1 levels compared to this negative control. So it was a nice result to see. And after this, we moved on to validate the PEG part of our nanoparticle using an already developed bispecific antibody in the group, like the anti-PEG, anti-EGFR bispecific antibody, just to validate the PEG component. So if you see this, you can see that the targeted nanoparticles are clearly having a higher cellular association compared to the non-targeted nanoparticles. So the PEG part of the nanoparticle is actually working fine. And the development of our anti-PEG, anti-transferrin receptor antibody is currently underway. So hopefully we'll get to that point soon. Meantime, we also did a biodistribution study using our nanoparticles and compared it against free oligonucleotides. So in summary, what we saw here is that, yes, the nanoparticles are actually having a longer in vivo circulation time, but there was no significant difference in the brain uptake between the nanoparticles and the free oligonucleotide. So this further emphasized the need for something like a targeting agent in order to improve the delivery of our nanoparticles into the central nervous system. So yeah, in summary, we are now on track to develop a non-invasive drug delivery system for the treatment of ALS or motor neuron disease using targeted nanoparticles. So this is the summary of my current project. And before finishing, I'd like to thank my supervisors and all these people who have helped me in so many ways. And yeah, thanks for listening.
Thank you so much, Gayathri. That was a brilliant way to end the session, and nice, and you kept to time, so it's even better. So let me see, we do have a couple of minutes for a couple of quick questions. And if no one wants to ask one, I will ask one because I definitely have one. So the previous slide that you just showed, could you just go back to one slide?
Yep.
So here with your flow cytometry, you're talking about using your targeting ligand, and how it's improving cell association. But when I look at my yellow band, I seem to have two, it seems multimodal. Is that correct? And is that because some don't have the targeting ligand, or how do you explain that?
No, yeah, so this is something that I got asked before. I said, but here I think I didn't use enough bispecific antibody. So if I increase the amount that I use, I should be able to get like a full shift. Since it was actually showing that the PEG part was actually working, I didn't go and do it. And I repeated the same experiment using a new technique called flow nanoanalyzer, and it showed the same thing. So through that, we were able to validate the PEG part. And once when we have the real bispecific antibody that I'm going to use, I'll definitely repeat the study.
Okay. Thank you so much, Gayathri. Okay, I don't think we have any more questions. So I will finish there and I will close this session. Just to note that we have asked all the panelists to stay on just because we're going to take a brief photo. But to everybody else, thank you so much for joining us. We had up to, I think, 94 people at one stage in this festival. So that is amazing. Please join us for the full 4 weeks because we have so many great talks. And I will be handing over to James to chair the next session. So thanks again and enjoy your weekend. And thanks, guys, particularly to Brett as well for starting us off, because that was a really great talk as well. So thank you and see you next time. As I said, panelists, please stay. Thanks. Okay, Nathan. Do your magic.
Hi everyone, if you just want to turn your screens back on. Cameras, have you got it?
Your screen's not on, Nathan, no.
So I'm still frantically adding everyone again.
Yeah.
This is a great idea. I thought you guys did a really nice job. I thought this was perfect.
Thanks.
Yeah. I think I really enjoyed it too, actually. I think such a broad range of science as well. And that was just so much to, go and think about. So I've missed.
You're doing it every week for the next every week for the next several weeks?
Yeah, every week for February.
Oh, that's
So,
awesome.
yeah.
Yeah,
Thank you
thanks
for
setting this up. I think it's great.
Yeah, well, I think we did miss the APS and having the opportunity to see all the broad range of science. Oh, I missed it. Everyone missed it. So I'm really glad we got to do something, actually.
I don't think my liver missed it.
Huh?
I don't think my liver missed the APS. I think it quite enjoyed having a year off from it. So.
And are you there? Can you turn your camera on quickly? What happened to Gayathri? She was still here. No, gone. They don't listen to you, are you, Georgie, at all?
What?
Nobody listens to you.
I know, right? This is why I'm saying I need to be more like James. I need to channel my James. So maybe I need to destroy my liver more.
Making the assumption that people listen to me.
They do.
I just rant until they get sick of me talking. So.
Okay, so I think nobody else listened to Georgie, so everyone do a quick smile and I'll take a quick screen grab. Perfect, thanks everybody.
Excellent.
All right, see you next time. And
thanks everyone
again
for participating, and thanks Brett for staying up late and giving that talk as well. So it was a really good way to kick off the whole thing, and hopefully the rest of the weeks goes smoothly as expected as well.
Yeah, thanks, James. Thanks, everyone. I really appreciate it. So hopefully I'll see everyone in person relatively soon.
Excellent.
Thanks for organizing, guys. Thanks a lot. Cheers.
Thanks, everyone. Yeah.